Okay, all right. So let us begin today's session. This is session number 8, and in this session, we are going to see the reactive power compensation and power factor correction. We will see the theory behind this, and then after having a quick recap of the reactive power compensation and power factor correction, we will solve two or three problems of GATE exam. So, what is the reactive power compensation? So most of the loads we are using in our households, we do not draw the power from the utility at unity power factor. We are having some lagging power factor that on which we are drawing the power from the utility. So we need to having the reactive power compensation at the load in itself. That is the we call it as reactive power compensation. If we see that the key idea of reactive compensation is to supply reactive power locally. Wherever the load is demanding reactive power, we supply the reactive power at that end only. This results in reduction of line losses which are equal to IR squared decrease and supply more load over the same wire. That means lower current allows utility to use a small wires. This also leads to improvement of bus voltage profile, that is voltage drop on the line is less, and the most important thing is that power factor correction. So these are the main advantages of the reactive by doing the reactive power compensation. First one is the reduction of line losses. That means you are having less amount of power flowing through the wire, that leads to the lesser amount of copper loss, that is IR square R loss. And second one is that supply more load over the same wire. As this reactive power we are not trying from the source side, we are giving the reactive power at the load end. So this allows the utility to supply power more from their side, so from the same wire. So this leads to lower current, allows it to use the smaller wires also. This is another advantage. And improvement of bus voltage profile, as the lesser amount of current is flowing through the wire, so this allows having lesser voltage drop across the wire. And the most important point is the power factor correction. This is also called as volt wire control. So what we see that if suppose we are having distribution substations, and we are it provides, these are the radial feeders, and these are distribution loads. So you can tell it as distribution substation, and these are loads that require both active and reactive power. So these are the passive type of loads. There are no distributed generation, because during in nowadays due to renewable energy integration, we may have distributed generations. So these are the passive type of loads only that demand both active and reactive power. So what we do is that in some at some nodes we place this reactive power. We put some reactive power source. We just put reactive power source at some nodes so that it does not draw reactive power from this distribution. It draws reactive power at lesser amount than whatever the reactive power demand having earlier. So this is the thing that we supply the reactive power locally. So this is called the reactive power compensation. Now there are different ways of reactive power compensation. Like you can use shunt capacitor, synchronous condenser, that is overexcited synchronous motor, custom power devices. In this, you know about DS STATCOM, DVR, UPQC, and distributed generation unit. We also called the most common term is DG units. So why among these different techniques we can do the reactive power compensation, and this reactive power compensation is used extensively by utilities, and you can by using the capacitor uh, you can just make the load's power factor to an arbitrary value. We will see the example for this, how you can use the capacitors to make the power factor at your base. So now shunt capacitor for the power factor correction. So by adding the capacitors, the reactive power component Q of the apparent power of the load can be reduced or totally suppressed, as we all know this point. Widening the capacitors, the reactive power component of the apparent power load can be reduced or totally suppressed. Let us assume a load is supplied with a real power P1 and lagging reactive power Q1 and apparent power S1 at a lagging power factor of cos theta 1. So this is the power triangle. In this we can see that whatever the load demand is, that all are drawing from the substation sides. There is no reactive power compensation at their load end. Therefore you can write cos theta 1 as P1 divided by S1, and S1 is the vector sum of active power and the reactive power. So you can write under root of P1 square plus Q1 square. Now we do the reactive power compensation, or we improve the power factor by using a shunt capacitor. So let us, when a shunt capacitor of QC kVA, so sorry here R is missing, QC kVAR is installed at the load, the power factor can be improved from cos theta 1 to cos theta 2. So the load demand is P1 plus JQ1, and this QC amount of reactive power is given by the capacitor. Now this reactive power drawn from the distribution substation will get reduced. So what will the reactive power for, coming from the distribution substation side? That will be Q1 minus QC. So whatever the power triangle we have drawn in the previous slide, we will add some, we will make that Q2 and QC in the same power triangle, so that we can see that how this power factor improves. So we can see that QC the reactive power, that is we are giving the reactive power locally to the load. So the net reactive power drawn from the distribution side is Q1 minus QC, that is Q2, and the apparent power also get reduced down, and this power factor is P1, it is as remain as it is. So how you can write cos theta 2? Cos theta 2 will be P1 divided by S2, and S2 will be P1 a square plus Q2 square, and Q2 square is nothing but Q1 minus QC whole square. So in this way you can see that this theta angle get reduced and power factor improves. Now let us see one example based on this power factor correction. So in this problem, assume we have 100 kVA load with power factor of 0.8 lagging and would like to correct the power factor to 0.95 lagging. What would be the capacitor size? All of you please try, and whoever is getting answer, type your answer in the chat box. Until here, if you have any doubt, you can ask. So I would suggest you that first make the power triangle. So power factor is given at 0.8 lagging. Cos phi is 0.8. If cos phi is 0.8, then sin phi how much it becomes? It becomes 0.6. And you can write this active power for the load. Active power for the load will be S into cos phi, that becomes 100 kVA into 0.8, that is 80 kilowatt, and similarly Q will be S into sin phi, that you will get 60 kVAR. Now first we will make the power triangle. So this is 80 kilowatt P, and before the power factor correction we are load is drawing load is drawing reactive power of 60 kVAR. So it is 60 kVAR. Now this triangle is this phi, this phi you can find. So this phi comes out as cos inverse 0.8, it will be 36.9 degree. And now we want to make the 0.95 lagging. So we can write power factor desired is 0.95. So phi d will be 5d, phi d is cos inverse 0.95. So this will be 18.2 degree. Yes, anyone got the
Nothing,
answer?
nothing, sir, nothing.
So earlier S is the apparent power.
31.22 is the Q. I think that is only the answer.
31.
0.22.
Okay, let us see. QC the we are doing the reactive power compensation so that we improve the power factor. This is the this will become 60 minus QC. So the desired phi d will be this, phi d becomes 18.2 degree. Now you just apply this trigonometry formula, any trigonometry formula. So we applied 10 so that we don't need to find apparent power. 10 18.2 degree will be 16 minus QC divided by perpendicular divided by base. So from here 60 minus QC will be 26.3, and therefore QC will become
33.69, sir.
yes 33.69 kVAR. This will be the capacitor size.
Yes, 33.7 because I found the Q for the Q. So we have to minus 60, I think.
Your voice is cracking little bit. Your answer is approximate same, so I think there will be calculator mistake or some approximation mistake. I think you will get that this answer. Now let us see this example of how we will see the effect of reactive power on the power factor. This is well-known example, and for this reference you can follow this Turan Gonen book that from electrical power distribution system engineering. This picture is taken from this book, and we can see that active power demand for all the load remains constant, that is 100 kilowatt. So you can write one point: active power demand for a load remains constant. We can see the 100 kilowatt. Now load is of inductive load, therefore we can see that with the reduction of power factor, the reactive power demand and VA demand of the load increases. In this case, first one is the resistive type of load, and all the rest is of inductive load. So load is of inductive load, therefore we can see that with the reduction of power factor, that power factor is 0.90, 0.80, 0.70 and 0.60. We can say that the reactive power demand and the VA demand, means apparent power demand of the load increases with reduction of power factor. So this is the disadvantage of having poor power factor. This VA demand is also increased and the reactive power is also gets increased. And this if you fix this active power, anyhow if this power factor is getting reduced, then it means that your reactive power is increasing, reactive power demand is increasing, and that's why your subsequently your apparent power demand will also increase. And now we will see another example for this effect of reactive power and power factor. In this case we have fixed the in the previous case we have fixed the active power constant. Now in this case we have fixed the apparent power constant, that 100 kVA. So in this case we have fixed the load kVA demand, load kVA demand is fixed, And with the reduction of power factor, we can see that the amount of active power we are taking, that is also getting reduced down. So we can write that with the reduction of power factor, the load is consuming lower active or real power, but reactive power demands will increase. But reactive power demand will increase. So these are two examples that from this cases we can see the effect of reactive power on power factor. Now we will see the concept of leading and lagging reactive powers. So what do you mean by this lagging and leading reactive powers? That depends on the direction of flow of reactive power. For the case of load with respect to load, if anyone is saying that power factor is leading, that means load consumes reactive power. Like we have considered load. So for load, if anyone is saying power factor is lagging, we all know about the voltage and current. That if his current phasor is lagging behind the voltage phasor, that means power factor is lagging. But you have to tell in the terms of reactive power. It means that power factor is lagging. It means that Q is positive and load consumes reactive power.
Means inductive load, sir.
Yes,
Load is RL load, sir.
yeah, inductive type of load. Load consumes reactive power. And by default, if nothing is written, then you have to consider this lagging reactive power. And other one can also say that load consumes lagging reactive power. For leading reactive power, you have to always consider, you have to always write, but a standard one is that whenever it is not specified, you have to consider the lagging reactive power. Now in similar way, one can also write in the terms of leading reactive power. So how you can tell about this leading reactive power? So here I have written this consumes. That if you write in the terms of leading reactive power, it becomes
Loads,
supplies.
load supplies reactive power.
Yeah, not reactive power. You have to at the time if you are writing leading, then you have to specify that leading reactive power.
Q less than 0, sir.
Load supplies lagging reactive power. So this all terms denote the same. That is Q is positive. Now if we consider power factor is leading. Power factor is leading. That means Q is negative. That means load supplies reactive power. Sorry, here I have written wrong. Load supplies leading reactive power. Load supplies reactive power, and you can also tell that load supplies lagging reactive power.
Leading reactive power, sir.
What?
That one leading power, sir. Load supplies leading reactive.
This is correct only.
Second, now you are writing, sir. Load supplies leading reactive power.
Load supplies lagging reactive power.
So
So how you will
it is
write?
correct. Load supplies lagging reactive power only. It supplies lagging reactive power only.
And just vice versa will be load consumes leading reactive power.
Correct, correct. This is correct.
Okay, okay, sir.
So this is the thing. I have written down a step by step. First thing you just remember, important thing if you want to remember, just remember first point and then make other assumptions. This point is very very important. Q is positive, then load consumes reactive power, and other points come from this point only. Means nothing written, that means you have to consider lagging reactive power only. So this is it becomes same. And if you want to write in the supply from, then means change the sign, then it becomes load supply leading reactive power. And for this also, if Q is negative, then load supply reactive power, that means load supply lagging reactive power. And if you change the sign supply and generation, then supply and consume, then it will load will consume leading reactive power.
Sir, power factor is lagging means load power factor.
Yeah,
Yeah.
load power factor, that is. And for I'm not telling here about generator side, but in the machines we use that if generator Q is positive, means that it delivers lagging reactive power, means it supplies lagging reactive power, but power factor remains as it is, and these terms will get changed in the in consume part. If it is lagging, then it becomes leading, and if it is leading, then it becomes lagging in terms of generator. So here in power system there is no requirement for that side. So for load you just keep this in mind. Now let us solve the some gate problems. This problem is from gate 2014. It is of 2 marks. So the question is that the complex power consumed by a constant voltage load is given by P1 plus jQ1, where P1 P1 boundary is 1 kilo greater than 1 kilowatt and less than 1.5 kilowatt, and Q1 belongs to 0.5 kVAR to 1 kVAR. A compensating capacitor shunt capacitor is chosen such that mod Q less than equal to 0.25 kVAr, where Q is the net reactive power consumed by the capacitor load combination. The reactive power in kVAr supplied by the capacitor is. So at one node it is a load connected whose demand is P1 plus JQ1 kVA, and one summed capacitor is for reactive power compensation connected to it, and this is the line that's applying the reactive power. So let us take it as QC. So P1 and Q1 given, and this Q is given 0.2 kVAr. So you can also write that this Q max that is coming from the line is 0.25 kVAr. It means so
That one is QC, no, sir. 0.25 kVA.
a compensating shunt capacitor chosen such that Q is less than 0.25 kVAr. So the whole for this whole it is 0.25 kVAr. I have written it down. So the limit is 0.25 kVAr. Then the reactive power supplied by the capacitor is how much? You have to find QC. QC will become here. Suppose you have taken this Q2. Then QC will become, it is better to write Q2 in terms of Q2. So Q2 will be Q1 minus QC. So Q1 will be, sorry, QC. QC will be Q1 minus Q2. And this a composition such that mod Q is given at 0.25 kVAr. So how much this reactive power should be maximum? QC max. You need to find QC max. So you have to take this Q1 max also. Q1 max minus Q2 limit. That is Q2 is only Q. So Q1 max is given as 1 and Q2 is Q that you can put 0.25 kVAr. That will give you 0.75 kVAr. So in this question, it is given that whole this combination, a capacitive shunt capacitance at that Q the net reactive power consumed by the capacitor load compensation. This Q2 it is given. So this is the maximum value. Q2 max will be 0.25 kVAr. That you cannot draw reactive power more than this value. If you write Q2 max, then it will be 0.25 kVAr. And Q2 is nothing but we have considered as Q. So in this way you can find this question. Yes,
Sir, how Q1 is 1 kVAR?
because suppose you have taken this lesser value. If you have taken this lesser value, then it just with it just get violated this value. More or less than this rule gets violated. This q2 max will be 0.25 kVr. If it is not, if you have to take the maximum value only, because if you have taken the lesser value, then it will be lower value. Then at lower value, suppose this q1 is gets increased, then the limit on this q2 max will gets violated. So in this way you have to think about, means you cannot fetch reactive power more than 0.25 kVr from the line. That is the thing. So you have to take the maximum value only. That in this way you can find this reactive power rating of the capacitor. Understood? Hello.
Yes, sir. This power will be lagging or leading.
This power will be QC max 0.7. This power is leading. No, this power is lagging. Sorry. You can write this supplies or in terms of lagging reactive power. You can write that sorry, capacitor supplies 0.75 kVr lagging reactive power.
Sir, capacitor always supply reactive power.
Yeah, that is the capacitor always supply, but if it is leading reactive power, then it becomes change. Capacitor consumes 0.7 kVr leading reactive power. That means in terms of lagging leading it will change, not always supply. You can tell that if you are writing in leading terms, leading reactive power terms, then it will be capacitor consumes 0.7 kVr leading reactive power.
Sir, why it cannot deliver leading reactive power? Because it is not generating.
What? Yes.
Sir, why capacitor is not able to supply leading reactive power?
Capacitor because it is the inherent characteristic of capacitor, means inductor always consumes lagging reactive power while this capacitor supplies lagging reactive power, and capacitor always consumes leading reactive power, means in the capacitor current leads the voltage. So that means capacitor consumes the leading reactive power factor. In terms of load always, what is the inherent characteristics of load? That is takes, means if you takes that is a consumption property. If you see that in capacitor current leads the voltage, that means capacitor consumes the leading reactive power, and in inductor current is lagging behind the voltage, that means inductor consumes the lagging reactive power factor, lagging reactive power. Okay.
Okay, sir. Yes, sir. Answer, inductor will supply leading reactive power.
Yeah, inductor will supply the leading reactive power. Yes, correct. That is,
Yes, sir.
I have written down here. Lagging power factor is lagging means that is inductive load. Here you can also write that inductive load, and here you can correlate your statement with these things. Inductive load supply leading reactive power, and inductive load consumes lagging reactive power. And if this is power factor is leading, then the type of load will be capacitive load. Now let us solve the next problem.
Sir, for this question, how much that capacitor consumes leading reactive power, sir? Consumes.
Consume 0.75 kVAR only.
That one supplies, no, sir.
Supply, that is the thing. If you are written in terms of supply and consumes, then leading and lagging term will also change. Here you are changing the leading term also. Means
Ah, yes, sir.
capacitor supply lagging reactive power. If you are telling that how much it consumes, then you have to tell the it 0.75 kVAR leading reactive power it will consume. Okay. Are you asking
Okay.
supply or consume?
So consume, sir.
Consume, then you have to tell that it is consuming 0.75 kVAR leading reactive power.
Okay, okay, sir.
Now let us see the next problem. This is the last problem, and this problem is a very nice problem, and it is asked in GATE 2017. I hope you all are able to uh, solve this problem. GATE 2017. It is of 2 marks. So the problem is that a load is supplied by a 230 volt 50 hertz source. The active power P and the reactive power Q consumed by the load are such that this is the limit for active power. It is more than 1 kilowatt and less than 2 kilowatt. Sorry, here will be Q. And for the reactive power, the limit is between 1 kVAR to 2 kVAR. A capacitor connected across the load for power factor correction generates 1 kVAR reactive power. Here you see nothing written. That means you have to consider lagging reactive power. Means capacitor is generating 1 kVAR lagging reactive power. The worst case power factor after power factor correction is. So here you have to make the power triangle first. So this is P, Q, and this is QC, P. This is active power, this is reactive power, and this is apparent power. In this question, it is asked that worst power factor. So this is, we all know that this is power factor angle phi. So we can write phi is tan inverse of tan.
That QC is upward now, sir, or downward, sir?
QC is downwards. If in many textbook you find that it is written like this, correct?
Yes, sir. Yes, sir.
But I means it is better to consider this side. Means here you have taken Q positive. That means lagging reactive power factor, and QC is negative. That means leading reactive power. So here it is Q minus QC, these terms, and this is compensated by react capacitor. Now this phi desired worst, it is asking worst. You can write YW. First we write this phi only, then phi is will be tan inverse Q divided by P. So if you want to get the worst power factor means power factor cos phi is minimal. That means phi should be phi
Maximum.
maximum. Phi should be maximum. So if you get phi maximum, then in terms of Q and P, it should be Q max
P
and
min.
P min. Here you write 5 rust, then 5W tan inverse Q max. Q max will be Q minus QC. So you have to take Q this one so that you get Q max 2 minus QC. QC is given 1 kVA reactive power. I will write one more. So it will be Q max minus QC divided by P min. Therefore, phi W will be tan inverse Q max is 2, QC is 1, P minimum is 1 kilowatt. So if we get phi more, then Q should be more and P should be minimum. Therefore, we can write like this. So tan inverse 1 will be 45 degree, that is worst power factor angle. Therefore, cos phi W will be
707.
0.707
0.707.
lagging. This is the answer. So B is the correct answer. It is your bis means you are considering Q top and Q negative. I consider Q top because Q is positive. Q is positive, that means lagging reactive power. That's why I am considering Q as top. That will not create confusion. In many textbook you also find that Q have taken down, but but it is but Q is positive for lagging reactive power. That's why I've taken up. That is more convenient. And Q, this for capacitor, Q is negative because it supplies lagging reactive power. So that's why I represent QC downside, and then it subtracted this lagging reactive power, and then you will get Q minus QC the desirable or burst. This here it is asking burst uh, angle. So this is you get. Okay. So any doubt?
Next problem, sir.
This is the last problem for today's session. I have put so less question today, only 2 problems today.
Sir,
So
in this we can
Sir,
expect that transient period, sir, and the switching period.
transient, uh, transient means what means
I mean, at the time capacitors turn on.
no, this is the steady state. All the conditions are in steady state. We have not considered transient state. Transient state means capacitor. If you see that the capacitor is a, like means you do you know the term supercapacitor? Hello.
Yes, sir. Yes, sir.
So for supercapacitor, we use for if you supply power in transient condition, then generally we use the supercapacitor. And this capacitor, battery, these are energy storage devices that we use for this steady state period. But for improving the profile, like sudden demand power, then we are using this supercapacitor. So we don't consider here this transient and out owl. These are means like a steady state condition only.
Okay, sir.
So any
Sir, please explain about how Capital Bank improve the power factor.
so this I have explained here. Capacitor bank be
The-
generally connected at the load end only. And if it is to the side, you may find the capacitor banks at the transformer. So generally in India you cannot find, but many places at European countries and other places they use the capacitor bank at this at the transformer only. So this capacitor bank, how you will get improve the power factor? This Q1 is the reactive power demand. So whatever the reactive power we are demanding, that is coming from the substation, and substation is taking power from the generator. So all in that we are we are demanding the reactive power. That means we are increasing this. We are increasing the amount of current also in the line. So this is avoidable. So what we will do? We will provide this reactive power locally. And how we will do? We will put the reactive, we will put the capacitor bank or another this another whatever this like synchronous condenser, custom power devices, and distributed generations, where we can just where we can tune the supply of active and reactive power. In distribution generation, it is depending on the control only. So based on the control, as your requirement, you can provide the active and reactive power. So by tuning that, we can generate the reactive power as our as on our bees. So here the generally with the capacitor bank on the distribution side. So here I've shown by this capacitor bank. And in the gate exam also many problems were asked on the capacitor bank only. They will not ask about this custom power devices and this distributed DG units. And many they may ask on this synchronous condenser, but generally they prefer for capacitor banks. So this capacitor bank, what what this will do? This will reduce the amount of reactive power coming from this line. So that means it improves the power factor. The power factor of a load remains as it is, but it removes the power factor of the that is fetching from the distribution substation. This is many students also get confused here. So power factor of load you cannot change. If a certain load, if you are providing at power at some voltage and frequency, this power demand will always remain same. They will demand this active and active power. This will not get changed. You are changing the power requirement from the generation side, from the substation side. So by providing this reactive power from compensation, you will improve this reactive power get reduced down, and uh, finally this cos theta will get improved. Okay, Antanu, are you able to get it?
Yes, sir.
Yes, sir. Yes,
And
sir.
sir,
Yes, sir.
whenever we will
Yes, sir. Yes,
connect
sir.
the capacitor bank, then it will consume active power. Active power.
How this capacitor consume active power? This
No,
is this is ideal capacitor. We are
If there
considering
were synchronous, I think if there were synchronous condenser,
uh,
we can assume power, active
yeah,
power in that.
yes. In that
That
case,
kind
the
of question
different,
also comes.
yeah.
Hmm.
Inductor and capacitor never consume active power. So, okay, Deepak, are you asking this problem? Are you asking this doubt, Deepak?
yes, sir.
Okay. So that's all for today's session. And any other doubt?
Sir, please share this PDF link.
So I am sharing this PDF link through this channel. You can go there, YouTube channel, and I am uploading on this uh, portal, NPTEL Gate portal.
NPTEL old videos are not being played.
Here you can go live mentoring session
I
and
am I am playing with my phone, but it is not. I am not able to play the videos, old videos, recorded videos. I don't know why.
this you can see here Saturday session. So
It's there only I've seen, but I'm not able to play that. Don't know why.
first or second
Yeah.
what session?
Any videos I cannot say open.
Then you use this laptop. In laptop I think there will not any problem.
Is there problem in mobile?
I don't know. There may be problem of Google Drive also.
Okay, okay.
If this problem persists, then you that's why I'm uploading on YouTube also for safety person. Means you have two access. You can access from here also and from this get portal from a YouTube channel also. And in the next session, we will see the per phase analysis of three phase system.
Sir,
Yes,
sir, could you please recommend that batteries topics are in NPTEL? Any lecture or videos?
battery.
Sir, battery topic.
Battery topic for electric vehicle charging.
No, sir. In general, in power systems.
In power systems, battery energy storage systems. You can refer this IT Madras lecture in PD lectures. I am not remembering the name, but IT Madras they have put
Which
lecture.
topic is this? Which topic is this? May I know?
Energy storage, battery energy systems, generally research topic. They will not the basic topic for this power
Because
system.
I have not seen. I have seen so many NPTEL videos. I have not seen any where battery or
Uh,
something.
there you will learn a state of charge and this C rating, other things from us by studying the battery. And generally, these are nowadays being commonly asked in interview and other all because of EV. But these are not gate topics. Battery is not gate topic.
Mhm.
Sir, smart grid concept, sir.
You are a BTech student or MTech student? Could I say?
No, sir. I'm preparing for Genco, sir. TS Genco.
Okay, TS Genco. A smart
In
grid.
that,
A, s- a smart grid. I would say you can prefer IT Roorkee lecture.
okay, sir.
Deep Lata Jain, ma'am, I think. Two professors have taken the course on a smart grid. IT Roorkee. You can prefer that.
Okay, sir.
Mm. But for a smart grid, they will not ask more this numerical type problem. They will ask theoretical type problem. If you have some common sense, then you can easily solve that. In
Yes,
numerical,
sir. Only theory part only, sir.
and if you are reading newspaper, then you are also able to solve that type problem. So that is the other thing. So thank you. We will see you all in the next session. Thank you for joining.